I wake up in the morning and think, I should write a numerical package for Tcl'. Odielib is actually a bunch of stuff from IRM that we needed to open source because we were writing a viewer for a client that we kind of guessed were going to take it apart as soon as they got it. So we decided instead to just take a lot of the graphical tools and generic math things and turn them into an open source project anyway. It's built on this modular build system. And I was talking about earlier the practical thing. I wrote a paper on it last year, but it comes packaged. You can either package it as a loadable extension, or I actually do provide a really nice mechanism so that you can tuck it into a static executable. So why did I end up using practical, not regular T? Well, I needed to make it work with our build system at work, and it's practical based. And many of the calls were already part of our system, and I really didn't want to have to rewrite all those build mechanics to make this a regular T project. So how does Odielib work? You just package require it, and you instantly get nifty things like vectors. And they look and act just like strings, except that in the background they're actually Tcl' values. There's also some cool stuff going on. You notice that I'm adding vectors of different sizes here, and it automatically makes the result the size of the biggest vector I fed it. And then I can even do things like feed it an empty string, and it pads that out to the number of zeros required for the operator I requested. In this case, vector XYZ is a 3x1 vector. We're using a Tcl'-based build system. I ended up having to recreate sort of like a very, very, very primitive version of what Critical does, because it was originally designed to write connective code for the kit, but a lot of my math routines ended up going in this notation. The next version of Practical is actually going to be able to read Tcl' files read Critical files right out, but that wasn't ready for the conference this year. And we're also going to be extending T beyond just making shared libraries in the future. Well, I kind of stumbled through that before. This is kind of what Practical looks like on the inside. We're all mad here. This is just, I'm going to try to rein in the craziness before we release this in the wild. But if you're looking at it from I'm building a new library perspective, it's C code that's just mixed in with your Tcl' code. And here I'm defining a new command. The stuff in blue is just the C, and then I'm back to Tcl' as soon as I close that bracket. And here we're just doing the simple, the state says it's 2 + 2, and we return 5. Then we can also inline C functions. And what I do is I make you give me a prototype so that I can put it in the appropriate spot in the headers, and then the body's the second argument. But again, this is just, it's a Tcl' function, it's a Tcl' command that is feeding in a data structure that's ultimately going to be inside of your C and header files. So here it's, up at the stuff in green is my prototype header, and basically anything that's admissible in C is admissible in that block. And then the raw body, and then we just sew them together at implementation time. Yeah. I just basically ended up writing a very brain-dead Critical. But that's only doing one tiny chunk of what Practical is doing. It's dealing with libraries, it's dealing with package repositories, so that's how that came about. So back to Odielib, how do we deal with numerical values? They're a special object type, and they represent vectors or matrices. Right now, it's optimized to handle 3D vectors being rotated by a 4x4 affine matrix. And within the C API, I actually make sure that there's enough room so that if you accidentally feed one type into where it's expecting another, you don't end up with any seg faults or crashes. And internally within the C API, all of the C API functions actually just take an array of doubles. So it makes it very nice for passing stuff back and forth. We don't do a lot of copying. It's just, I throw it over the wall, stuff comes back, and then I can figure out whether I'm going to pass a copy to Tcl or I'm going to rewrite the value that came in. So we can do pass by reference and pass by value. And it just, so it, pass by value is I have A, I have B, I generate C. And what we do is we've got some operators inside of Odie that take the value and copy it into some known location. So here, vector x, y, z are actually just double threes. And I am using the Odie get vector x, y, z from Tcl'2017 to copy the value out of the Tcl'2017 and into this array that I know the location. I don't have to worry about allocating because as soon as this ends, C is going to throw it away. And then when I'm done, I take this new C that I created and I feed it back to the interpreter as a brand new Tcl'2017. That's not efficient for every case, so we also do a pass by reference. So here we've got A and B, and I can give it equivalent of an inker operator, where I feed it instead of the value A, the variable A. And what will happen is B will be added to A. Nothing gets returned because A is now this new value. And on the C API level, instead of using the copy operator, which gets the known type from inside the object, I instead return this generic form of the matrix where I'm looking at the actual double array on the inside. So that's why I'm using the Odie get matrix from object. What that's doing is it's going into the Tcl'2017, it's turning it into one of these matrices that it's not already, and then from there I can pull out the array of doubles that it's managing for me. I perform my math operation, and then instead of returning a value, what I do is I just invalidate the string representation on the Tcl'2017 that came into me, and I return. And because the underlying storage for this is an array of doubles, I don't actually have to tell anybody that I changed it. It's gone, and then if you, yes?
Why hasn't the set from any routine of your object type already done the invalidation?
I don't know. I'm kind of,
okay.
I'm new to this stuff, so if there's,
Okay.
Well, actually, the setup from object wouldn't know anything about it because I modified it after I did the get from object. So what happens here is vector xyz add is taking the A matrix as the result. It took the A matrix also as one of the operators, and then it added B to that. So I modified.
I get it.
Yeah.
Sorry.
Yeah. So that's why. Okay. Great question, man. At least somebody's paying attention. All right. What's really cool is that we can now do a bunch of batch operations in Tcl without incurring a heck of a lot of overhead. So here I've got a very, I'll call it rudimentary, game engine sort of thing, where we're doing rotation and we're applying thrust and we're making things spin around. So this is just a very, as much as I could actually make one fit onto a slide and have it somewhat readable, physics simulation. And what's going on is we've got a location, we've got an attitude for the physics object, we've got a spin we're applying to it, we've got a thrust we're applying to it, and a velocity. And as this thing is moving along, it's spinning and thrusting, and you're just going to kind of watch it go whee! Or you would if I had time to prepare an interactive demo like that. Instead, I just output it to the screen. But there we've got the thrust. It's processing at the same time as thrusting, and it looks basically, if you could map it out, it would look kind of like that. But we're doing that in a discrete time simulation using just Tcl code, but it's accelerated because we're doing all the hard stuff in C. All right, now it doesn't just do matrices. I also have a bunch of really nice geometry routines for breaking apart convex polygons. There's a segment set system so that you can take arbitrary vectors and synthesize polygons from that. There's set operations for polygons, so you can do, take a series of tiles and figure out how they work in progress. Yes. I should put an obvious flaw in my demonstrations. All right, so future directions. Actually, I had a lot of well, I had one person talk to me on the Tcl' chat after having read the paper, and there was an idea on how to come up with a better standard for a lot of the names in this. So there's hundreds of functions I'm creating, and at this point I had about a dozen namespaces that were being created out in global. So I'm going back through and working out a more coherent naming system, because this is about 10 years worth of code that, I was just kind of seeing the light of day for the first time. Also, the next version of Practical is actually going to be able to read critical modules, so you're not going to have to learn Sean's insane syntax anymore. You can use Stephen Andreas's crazy notation. And also a lot of my regression tests right now, there's I've got some standard Tcl regression tests, but some of them are still eyeballing because I'm still trying to work out the math on some of the functions. Now, at first glance, it seems like a lot of duplication of what Vectel's doing, but he's really targeting something else. Vectel is an expression engine, and Odielib is more designed to perform batch operations really fast. I also don't need to patch the core, and Vectel allows you to do more than 2 dimensions, so you have actually n dimensions that you can work with. So it's much more for doing high-level tensor sort of arithmetic, and Vectel is really not ideal with 4x4s, and then I just kind of make them smaller or bigger, depending on what you expect the output to be. All right, I maintain a fossil repo that is online, and it's got a ticket system for all the bugs that you're all going to find. And if you need to get a hold of me, there's my email. Gerald.
Sean, how, aside from you did it, how is it different from the vector package in RBC, the old VLT stuff?
I have no idea. I haven't used it.
Okay. Any other questions? Okay, well, thank you, Sean.
All right,
I guess
thank
we
you.
will move ahead. And our next speaker